Video, we're going to start talking about a new chapter, which is chapter 5. So, chapter 5 talks about sequences and series and their convergence and divergence. So, we finished talking about integrals, and now we're going to start talking about series. So, chapter 5 and 6 is all about series in general. So, the first thing that we're going to start talking about is sequences. So today we're going to learn how to find a formula for a sequence, how to find the limit of a sequence, and we want to determine whether our sequence diverges or converges. So let's start with the terminology of sequences. What is a sequence? So we're interested in talking about infinite sequences. So a sequence is an ordered list of numbers where we have these forms. So a1, a2, up to an, up to infinity. Each one of these ai's is called the term in the sequence. And the 1 to up to n, up to infinity, these are my indexes. Okay, so the notation of an infinite sequence, looks like this. So usually the sequence starts at 1 and goes up to infinity, but for simplicity, we're just going to write it as this without n equals 1 and infinity. Okay, so sequences could be defined by an explicit formula where my an is described as a function which is defined over a positive integer. So my an would look like f of n. So I have an explicit formula for my terms, or I can have a recurrence relation between my terms. So a recurrence relation is where one term of the sequence is given, usually the first term, or as we call it, the initial term, and then the subsequent terms are defined depending on that term. So let's see this example and see how we're going to define this sequence using explicit formulas and using a recurrence relation. So as you can see, my sequence is going 2, 4, 8, 16, 32. And if you notice a pattern here, all of these numbers are a multiple of 2. Or if you can think about it, a1 is 2, so it's 2 to the 1. a2 is 4, so it's 2 to the 2. a3 is 8, 2 to the 3, and so on. So the pattern that we notice here is my nth term is going to be given using an explicit formula of 2 to the n. Because if you notice here, I have a 3 and a 3 here, 2 and a 2 here, 4 and 4, and so on. So the explicit formula for my nth term is 2 to the n. Or we can think about it differently. If you think about it, these terms are related by this term is twice as the previous term. This term is twice of the previous term of it. So the nth term here, we could express it in a recurrence relation where the initial term is given by a1 is equal to 2, and then all other terms after it is a multiple, or a multiples of 2, like it's twice the previous term. So if you want to represent it as a recurrence relation, your nth term is given by 2 times the term after it. So here, for example, the 8 is 2 multiplied by a of 2, because I know a of 2 is 4, so 4 times 2 is just 8, so you get a3, and so on. Okay, a few notes. The index for my sequence doesn't have to start by 1. I can start my sequence at 3, at 4, and whatever. Doesn't matter. And each term in, each index n is defined by a specific value. So I can't have for n equals 2, I have 2 values. Each n has a specific value, and if we graph the sequence, it's going to consist of points n, an. Okay, so that's the definition of a sequence in general. It's just obvious. Now we have two types of sequences that we're going to learn. We have arithmetic sequences and geometric sequences. an arithmetic sequence is where the difference between every two pair of terms is the same. So for example, if you look at this sequence, I have 3, 7, 11, 15, 19, and so on. You'll notice that going from one term to the other, you're adding 4. If you want to use a recurrence relation, this means that I'm taking my initial value, a equals 3, and then the nth term is going to be the term before it, and I'm adding 4. So it's just an minus 1 plus 4 for n equals or bigger than 2. Or if I want to use an explicit formula, it's going to be the initial term plus the difference multiplied by n minus 1. Once you simplify, you're going to get 4n minus 1. So if you want to write it as, like if you want to write a general formula for arithmetic sequences, it's going to be a plus an is going to be a plus n minus 1d. A is my initial term, and d is the difference between the terms. For example, it was 4 here. So for any arithmetic sequence, you can use this formula to find an explicit formula that's going to describe your sequence. Now, a geometric sequence is a sequence where we have a ratio between the terms. So let's look at this example. 2, negative 2 over 3, 2 over 9, and so on. If you notice, the numerators are all 2. Doesn't matter. But if you look at the denominators, I have 3, 9, 27, 81. So all of them have a ratio of 1/3. But since I have a negative here, so the ratio of any term to the preceding term is negative 1/3. If we want to use a recurrence relation, we always start with the initial term, which is the first term, and then your an would be the ratio multiplied by an minus 1. Or if you want to think about it as an explicit formula, you can write it as, since I have a 2 in each term, I have to have 2 multiplied. Then you take the ratio and raise it to n minus 1. So here, a geometric series has the form of c r to the n, where r is my ratio. Let's try this example, and let's try to find an explicit formula for this sequence. So when you have fractions as your terms, you always have to think about the numerators and the denominators. You find the formulas for each one separately, and then you combine it in the end. You also have to be careful when you have a negative sign. If I'm going from positive, negative, positive, negative, it means I have a factor of negative 1 to the n, or negative 1 to the n plus 1. So how do I choose whether it's n or n plus 1? It all depends whether my odd terms are negative or my even terms are negative. So here, if you look at it, I'm starting at 1. 1, 2, 3. So all of my even terms are negatives. So if my even term is negative, the factor is going to be n plus 1. Because here, if you plug in 2, for example, 2 plus 1, that's 3, so I'm going to get a negative. If my odd terms are negative, then the factor would be negative 1 to the n. Okay, perfect. Now we start with defining the factor of negative if we have negatives. Then we're going to start working with the numerators, then the denominators. If you look at the numerators, they're all 1s, which means the sequence that represents, like the formula for the sequence that represents the numerator is just 1. Now let's look at the denominators. I have 5, 7, 9, 11. So here we all have odd numbers of the form 2n plus 3. So the denominator has the formula of 2n plus 3. Now you can find this using the arithmetic sequence formula that we've talked about before. So now, if you want to write an explicit formula for the whole sequence, it's going to be negative 1, n plus 1, then multiplied by 1, which is the numerator formula, and then over n plus 3, If you want to simplify, this is negative 1 plus 1 over 2n plus 3. Now let's try it here. We want to find an explicit formula for a recurrence relation. My a1 is negative 4. To find a2, I'm just going to apply this relation. a2 is just a1 plus 6, so that's negative 4 plus 6, so that's 2, which is 2 times 1. Similarly, a3 is just a2 plus 6. I know a2 is 2, so that's 2 plus 6, 8, which is 2 times 4. And similarly, for a4, I'm going to get 2 times 7. Now, to write an explicit formula, we have 2 in all of them. So I know that in the formula, in the end, an must have 2 in it. Now I want to find a pattern for the numbers that I have left. I have negative 1, negative 2, 1, 4, and 7. So negative 2 has a difference of 3 between it and 1. And then 1 and 4 has 3, 4 and 7 has 3 also. So this is an arithmetic sequence. So we know that an arithmetic sequence has the form as a plus n minus 1d. Now a is my first term. So my first term is just negative 2. Then my difference is 3. So to find a formula for my arithmetic sequence, it's going to be negative 2 plus n minus 1 times 3. If you simplify, you're going to get 3n minus 5. So the general formula for this recurrence relation is going to be an is going to be 2 multiplied by 3n minus 5 for n bigger than or equal to 1. So we've done the first part of finding a formula for a sequence. Now what happens if I want to find the limit for my sequence? So the limit of a sequence, you just take the formula that you got for your an and you take the limit for it directly. We say that my sequence is convergent if my limit of the sequence is convergent, and the sequence is divergent if the limit of that sequence is divergent. So let's try this example. I have 1 minus 1/2 to the n. If I want to determine whether this sequence converges or diverges, I need to take the limit. Now, if you take the limit of that, this would go to 0. So I'm going to have the limit to be equal to 1. Since the limit has an explicit value, the sequence converges. Now, what if I have a function that's defining my sequence? If an is determined by a function f of n. So to determine whether your sequence is convergent or divergent, you just take the limit of your function. If that function has a value and it converges, then my sequence converges and it has the same limit. So let's do a quick reminder. If I have a limit with r to the n, if r is 1, the limit is just 1. If r is a fraction between 0 and 1, it converges to 0. But if r is bigger than 1, then this limit diverges to infinity. So let's do the same example, but without the 1 minus. If I have 1/2 to the n, the related function to that is just 1/2 to the x. Now, f of x converges because if you take the limit of 1/2 to the x, this is just 0. Because if you apply this rule, r is 1/2, which is between 0 and 1, so the limit is just 0. So the sequence must also converge, and it converges to 0. Now we have these limits laws that we already know from Calc 1. If I have a number, it's just the number. If I have a constant, I can take it out. I can distribute the limit over the sum, and I can distribute it over the multiplication and division. So let's try this example. If I have this limit, I can distribute it and take the number out. So this is 10 minus 5 times this is 0, so it's just 10. Then the sequence converges to 10. If I have this limit, I can distribute this is going to be equal to. So now here, if you apply L'Hopital's rule, we're going to get a 0. Then e to the n also goes to 0. So this is 0 plus 0, which is 0. So this sequence also converges, and it converges to 0. Okay, so let's look at this theorem. If I have a sequence that converges to a certain value L, if I have a continuous function at that point L, then f of a of n also converges, and it converges to f of L. Let's see where this theorem might be helpful. If I have this sequence, so instead of taking a limit and evaluating and doing a lot of steps, if you think about it, what's inside of here, let's assume it's my a of n that's here. So I'm going to define a of n as 2n plus 1 over 8n. Then my function is the outer function, which is the square root of x. Now, if you take the limit of your an, this is going to be 2 over 8, which is 1/4. And my function is continuous at 1/4. So this whole sequence by theorem converges, and it converges to f of L, which is f of 1/4. So this is just 1/2. So my sequence converges to 1/2. Now the last theorem that we're going to talk about today is the squeeze theorem. So the squeeze theorem is very helpful when you're able to find an upper and lower bound for your sequence, and you know the limits for each one. Once you're able to find the limit for each one, the limit for your sequence that you want to evaluate is going to be the same. So let's look here. If I have sequences A, B, and C, and we have this inequality, so Bn is squeezed between An and Cn. If the limit of An and the limit of Cn is equal, and it's equal to L, the theorem tells us that my sequence Bn converges, and it converges to the same value. So let's try it with this sequence. I have sine of n over n cubed. Now, if you want to find the limit here, it might be a bit difficult. So what we're going to do is we want to build our sequence using facts that we already know. I know that sine of n is between -1 and 1. That's the range of sine. Now, if we want to build the sequence that we have in the middle, I need to divide by n cubed. Now, using the theorem, if these two converge and it converges to the same point, then the sequence that I already want to know the value of converges to that point. So now if you take the limit of this is going to be 0. And the limit of 1 over n cubed as n goes to infinity is also 0. So by theorem, the limit of sine of n over n cubed must also converge to the same point, which is 0. So this theorem is usually helpful when you know the range of a certain thing and you're able to squeeze it between two values. So it works well with sine and cosine, for example. So these are some suggested problems, and you can do these problems from Lumen Homework 4. If you have any questions, please let me know.